Welcome back to the deep dive. Today, we're not just looking at blueprints, we're stepping right into the heart of some really high-stakes, world-class engineering strategy.
That's right.
Our mission today is, well, it's pretty critical. We're going to define the core energy heart of a Formula Student electric race car, the high-voltage accumulator system, or HVA.
And this is a really special deep dive. It's based on a formal statement of requirements, an SOR, that was put together by a senior powertrain architect.
And it was designed specifically for a new university team, right?
Exactly, to guide them. This isn't just generic advice you'd find anywhere. This document is a strategic roadmap for a team to achieve world-class competitive status, right out of the gate.
Especially if you're planning to go up against the giants. The teams at, say, Formula Student Germany, FSG.
Especially then, yes. The sources we're using, this incredibly detailed technical spec, they make it crystal clear. This is not about just throwing high-power parts together and hoping for the best.
It's all about strategic design.
It is. The whole strategic landscape in FSE has fundamentally shifted over the last few years.
Oh, so?
Well, it's moved far beyond what the document calls simple power stacking.
Oh, which is just jamming in the biggest cells you can find.
Pretty much. The new battleground, the new competition, is defined by three tillers that are all interconnected. First, extreme energy density. Second, maximizing your system packaging efficiency. And third, maybe most importantly, achieving extreme reliability.
So the HVA has to be more than just a power source.
It has to be a performance multiplier. It has to allow the driver to fully exploit the vehicle, not become a liability that's just waiting to fail you on the endurance run.
I have to say, I love how the structure of this requirements document, it mirrors top-tier professional consulting work. It feels very methodical.
It is. It's engineering strategy first, component second.
And what's the guiding philosophy behind that?
To achieve this level of precision, the document uses a professional thinking methodology pioneered by firms like McKinsey.
You mean the MECE principle?
The MECE principle, exactly. Mutually exclusive, collectively exhaustive.
So breaking it down, that means every single aspect is covered exactly once with no overlap, and the whole project is accounted for.
Precisely. It forces a systematic approach. We're breaking this massive task of building an HVA into 5 distinct, manageable, and highly optimized core subsystems.
7.1 through 7.5.
Right. Covering mass, cell technology, electrical topology, structural integrity, and, of course, thermal management.
So before we even think about opening a CAD program or choosing a single fastener, the guidance insists on starting with a strategic blueprint. It's called engineering by hypothesis. What does that strategy actually buy you?
Hypothesis-driven development, or HDD, it's absolutely critical. FSE teams, especially new ones, are operating under immense constraints. Time, budget, manpower, you name it.
So you can't afford to waste time.
You cannot afford long, wasteful iterations. HDD forces the team to avoid what we call designing in the dark. You base every major decision on a verifiable assumption.
So you formalize what you believe is the most efficient path forward.
Exactly. And if that core assumption, that hypothesis, is proven wrong early in the process, you pivot immediately. You save months of wasted effort and a huge chunk of your budget.
The SOR outlines 3 core hypotheses for this HVA 7.0 system. Let's start with hypothesis A, which feels like it addresses the foundational electrical architecture.
It does. Hypothesis A bets heavily on the concept of high voltage, low current. Specifically, we are mandating a 144 series cell configuration.
Okay.
And the core assumption here is this. The weight savings you gain from using lighter bus bars and thinner wiring because you're running less current will ultimately outweigh the complexity penalty.
What's the complexity penalty?
The penalty of designing, programming, and managing a much more complex high-voltage battery management system, the BMS.
That sounds like a major risk. You're accepting a higher technical hurdle, a more complicated BMS, for an unproven weight saving. Is that really a smart trade-off?
It's the defining calculated risk of a world-class system. And it's smart because the physics are completely on your side. Let's break down the why.
Please.
Power loss in any conductor is defined by the formula IIR. That's current squared times resistance.
Right.
So if you double your system voltage for the exact same power requirement, you get to have the current. But because that current term is squared in the loss equation.
Ah, I see. You don't just have the loss, you quarter it.
You immediately quarter the resistive thermal loss. So reducing the current by 50% means you're only generating 25% of the heat in your wires and bus bars.
That lets you use much thinner conductors.
Exactly. And you can strategically swap traditional dense copper for much lighter materials like laser-welded aluminum,
Which has a knock-on effect.
a huge one. Less resistive heat means you need less cooling for your high-voltage components and the bus bars themselves. This leads to a secondary cascade of weight reduction across the entire cooling system. That's where the savings truly accumulate and just crush the complexity penalty of the BMS.
Okay, hypothesis B. This seems to shift from physics to logistics and operational strategy. It's all about this strict 6-kilogram module limit.
This hypothesis is, it's born from painful competition experience. I've seen it happen. When you design a module that is compliant with the FSG rules, say a 10 or 12 kilogram segment, you inevitably need specialized equipment in the pit lane. You need gantry cranes, dedicated carts, or you need 2 strong people just to lift and manage the module safely.
Right.
Hypothesis B states that by limiting the segment weight to 6 kilograms, we can completely eliminate the need for any of that specialized equipment.
And the operational advantage of that is?
Speed and simplicity. It transforms what is often a complex, high-risk maintenance task like replacing a damaged battery segment into a fast, single-person operation.
Which means you can reduce battery replacement time to, what, under 30 minutes?
Under 30 minutes in the pit lane. In that frantic, high-pressure environment of competition and scrutineering, that speed can literally be the difference between making the next event and just going home.
And finally, hypothesis C. This deals with the physical reality of the chosen cell technology, specifically the persistent headache of pouch cell swelling.
Soft-pack lithium polymer cells are absolutely essential for power, but they breathe.
What do you mean by breathe?
As they charge and discharge, and certainly over their lifetime, they permanently swell, sometimes by 10% or even more in thickness. And the force of that swelling is immense.
So you can't just ignore it.
You can't. So hypothesis C is an engineering leap. We assume that the compliant structural materials inside the foams, the internal structure, can completely absorb this internal expansion force.
So instead of fighting the force, you're managing it.
Precisely. If
Yeah.
we can rely on the cell stack itself, held under a very precise amount of structural preload to become a stiff structural beam, then we can design the external box walls to be much, much thinner.
That's a huge philosophical shift.
It is. Instead of designing a heavy, rigid enclosure to contain a soft battery, we turn the battery stack itself into a structural element that helps support the enclosure. This is where you unlock major material and weight savings.
This whole strategic setup leads us directly to resource allocation. You mentioned time and budget are tight. So using the Pareto principle, the 80-20 rule, where must a new team focus its resources?
The SOR is it's completely uncompromising on this. 80% of your performance advantage in the HVA system will come from optimizing just 20% of the critical decisions.
And wasting time on non-critical components is?
A guaranteed path to mediocrity, absolutely.
So what is that critical 20%?
Yeah.
Where do you put your best people?
3 areas, and they map directly to our subsystems. First, cell selection, which is subsystem 7.2. It's foundational. Your power density is paramount.
Okay.
Second, the development of the leak-free cooling plate process. That's 7.5. And why is this so critical? Because a single drop of coolant inside that high-voltage box means an immediate isolation fault. DQ, event over.
So it has to be perfect.
100% reliable, which makes its manufacturing process incredibly complex. And third, the composite layup design for the enclosure itself, subsystem 7.4. It's technically demanding to simulate it correctly and then manufacture it to withstand those 40 brine loads.
So conversely, where can a smart resource-constrained team afford to use standard off-the-shelf components?
That's the conventional 80%. Things like standard, high-quality fasteners, general electrical connectors for your low-voltage systems, exterior coatings, non-structural components.
So the message is clear.
It's a strategic imperative. Do not waste your top structural engineer trying to topology optimize the washer on a non-critical bolt. Buy the standard part, ensure it's high quality, and divert every single ounce of engineering brainpower to optimizing the cell, the cooling integrity, and that 40-gram enclosure.
All right, now that we have the strategic framework, let's dive into the first of those subsystems, 7.1 mass. And the target here is, frankly, it's aggressive. A single accumulator segment mass must be strictly less than or equal to 6.0 kilograms.
This is the first demonstration of what the document calls an engineering benchmark strategy.
What do you mean by that?
Most major FSG rule sets, they allow segments up to 12 kilograms. And that 12 kilogram limit often aligns with a rule about the maximum energy per removable segment, typically around 6 megajoules, which is about 1.6 kilowatt hours.
So by setting this internal, non-negotiable target of 6 kilograms.
The team is deliberately engineering superior power density and packaging efficiency. We are forcing a twofold innovation jump compared to what average teams are doing.
And we should clarify this 6 kilograms is the limit for one segment, right? Not the whole accumulator.
Correct. The total accumulator mass is still substantial. We estimate it between 55 and 75 kilograms, and that's the figure you have to use for the critical safety calculations for impact loads.
But why this aggressive halving of the segment weight? What's the rationale?
The strategic rationale breaks down into 3 interconnected areas. It creates this chain reaction of benefits, and it all starts with vehicle performance.
Okay, let's start there. Vehicle dynamics. How does a lighter module actually improve the car's handling?
Mass, especially high-up mass, is the mortal enemy of handling. It's just physics. Formula student engineers are in a constant battle to minimize the vehicle's yaw inertia, or moment of inertia, MOI, and the center of gravity, or cog height.
Yaw inertia being how hard it is to get the car to turn.
Right. How hard it is to get it to rotate, and then how hard it is to stop that rotation.
And if the mass is all clumped together in the middle, it's easier to turn, but if it's spread out, it's sluggish.
You've got it. Larger, heavier modules, say 12 kilograms, they consolidate mass in a few big chunks. This really limits your placement options. With 6-kilogram segments, you gain much finer granularity.
So you can place them more strategically.
You can place those segments with incredible precision, maybe lower along the center line of the chassis, or distributed perfectly between the front and rear axles to get the absolute lowest cog and tune that MOI perfectly. That's how you maximize cornering speed and responsiveness.
The second rationale is the physics of safety, which you mentioned has a massive dividend on that 40-degree load requirement.
This is a huge and often missed insight in the SOR. The safety rules mandate that the structural enclosure must contain the segment during a 40-gram deceleration.
So a crash.
A big crash. Now, if you have a 12-kilogram segment, it generates about 4,708 newtons of force in that impact. By cutting the segment mass to 6 kilograms, you reduce that maximum single-point impact force to just 2,354 newtons.
You've cut the force in half.
Exactly. So by engineering the segment to be light, you dramatically lower the structural burden it places on the rest of the car, on the rest of the box.
Right, so you're designing the entire supporting structure, the internal walls, the mounting fasteners, all for half the load.
Precisely. And this allows for what we call system-level secondary weight reduction. The lightweighting starts with the segment, but it ripples out to make the entire chassis lighter and, frankly, safer.
And the third rationale connects back to hypothesis B, pitlane efficiency. This is the real-world operational difference maker.
Oh, I remember this vividly. I was watching a team at FSG struggling with a large 12-kilogram segment change. It was painful to watch.
What happened?
They needed a dedicated wheeled cart, 2 engineers, and they were trying to meticulously align this module with a crane setup, all while the clock is ticking and the pressure is mounting.
And how long did it take?
Nearly an hour. And it introduced a massive risk of dropping it or misalignment. A 6-kilogram segment, on the other hand, can be handled by a single engineer with minimal specialized tools. It's like changing a server hard drive in a data center.
Quick, clean, mistake-proof.
Exactly. This boosts your operational readiness, and it allows the team to use their precious time for other critical tasks during technical inspection and the event itself.
But achieving this 6-kilogram target must require some radical material choices, especially when you look at the mass budgeting analysis. The cells themselves eat up over 3/4 of the budget.
That is the 1.23 kilogram challenge.
Yeah.
And it is brutal.
Break that down for us.
Okay, so if we assume an 18 series, one parallel configuration, that's 18 S1P, and a high-performance cell weighing about 0.265 kilograms, the cells alone account for 4.77 kilograms.
Leaving just 1.23 kilograms for everything else.
For everything else, the cell frames, the bus bars, the insulation, the cold plate, all the associated electrical components, every single gram has to fight for its existence.
So how is the team mandated to achieve that 1.23 kilogram limit for the structural parts?
We start with the cell frames. They're budgeted for a mere 450 grams. This immediately rules out things like injection molded plastics or simple CNC aluminum.
So what's left?
The SRR mandates advanced 3D printed materials, specifically carbon fiber nylon PA12CF or Ultem 1010. These materials offer incredible strength-to-weight ratios, and critically, the design must use topology optimization.
To remove every last bit of unnecessary material.
Every unnecessary wisp of material, ensuring the wall thickness is 1.5 millimeters or less. This is lean engineering taken to the absolute extreme.
Okay, the bus bars are next, budgeted at just 300 grams. This means moving away from copper, doesn't it?
It absolutely does. The strategic shift is mandatory. Laser-welded aluminum bus bars.
But aluminum has lower conductivity than copper.
It does. It has about 60% the conductivity of copper, which means for the same cross-sectional area, it has higher resistance. However, aluminum has only 30% of the density of copper.
So it's a trade-off.
It's a calculated trade-off. By accepting a slight, manageable penalty in resistance, you achieve a 50% overall mass reduction compared to an equivalent copper solution. And that weight saving is deemed far more valuable to your lap time than the minimal increase in IRR heat generation.
And the cold plate, the core of the thermal management system, has a hard limit of 350 grams. How do you build a heat exchanger that strong and that light?
It requires thin-walled microchannel aluminum, and you have to use a process called brazing.
Brazing.
It's a metal joining process. You use a filler metal that melts at a high temperature but still below the melting point of the base metal. This creates extremely strong integrated structures like you'd see in high-end automotive radiators.
And that avoids the weak spots of welding or bonding.
Exactly. It allows the walls to be incredibly thin and lightweight while remaining completely leak-free.
Let's circle back to the risk. You mentioned that hypothesis C relies on using the cells as a structural element. Doesn't that just sound like you're shifting the failure point from the frame to the cell itself?
That's a really important question, and it reflects a common skepticism. The risk is managed through a controlled preload.
Explain that.
You're not simply throwing away the frame. You're using precision tie rods to apply a controlled, constant compressive force to the soft pack cells. When they're compressed, the cells gain significant stiffness. They effectively turn the entire stack into a composite structural beam that's capable of handling the inertia forces.
So the 3D printed frames are just for positioning them?
They're for positioning the cells and providing the initial insulation. The preloaded stack does the bulk of the work for the 4-degree load management. Now, if the preload is wrong, yes, the cells will be damaged. But if it's right, the weight saving is just massive.
Let's move to subsystem 7.2, cell technology. The document is very clear here. It says that high C-rate soft-pack lithium polymer cells, LiPo cells, are the only choice for extreme racing performance.
Yes.
Why such an absolute ruling? Why can't a team use the more common cylindrical cells like the 201700s we see in road EVs?
Because FSE is a sprint competition, not a range competition. That's the key difference. While cylindrical cells, the 18650s or the 201700s, they excel at energy density and long cycle life for road cars, they simply cannot deliver the instantaneous current you need for the competitive dynamics events.
Acceleration in autocross.
Exactly. You need explosive power coming out of every single corner.
So it's a question of internal resistance and power density. Explain why the pouch cell wins that fight so decisively.
It all comes down to the internal architecture. Cylindrical cells use winding technology. The cathode and anode layers are rolled up like a Swiss roll inside a rigid metal can. The current has to follow that long winding path, which creates internal resistance. Pouch cells, the ones used here, utilize stacking technology. The layers are stacked flat, like pancakes, and the current can flow instantly across these wide, flat tabs.
So it's like a high-speed freeway versus a winding mountain road for the electrons.
That's a perfect analogy. This stacked construction minimizes the internal distance the current has to travel, and the result is an extremely low DC internal resistance, or DCIR, typically below 1.5 milliamps.
And that low resistance translates directly into power output.
Massive power output. We're talking about cells that can support sustained 45C discharge rates and pulse rates up to 90C. Your standard road car cylindrical cell might only manage 10C, maybe 15C. For a race car that needs 100 kilowatts instantly, the high C rate of the soft-pack LiPo is simply non-negotiable.
Beyond just the raw power, there's a major advantage in thermal management, which is crucial for surviving that 22-kilometer endurance race without overheating.
The geometry is key here. Pouch cells are flat. They give you a large, flat surface area that is designed for direct contact coupling with the cold plate. The heat flows efficiently and directly through this huge interface.
Right.
Now, contrast that with cylindrical cells. The heat has to travel radially through the inner core, through a viscous electrolyte, then through the steel casing just to reach the cooling medium. It's an inefficient, bottlenecked thermal path. It makes uniform cooling far, far more difficult.
And Subsystem 7.1's focus on packaging efficiency also benefits from this pouch cell choice.
Oh, absolutely. Pouch cells pack nearly perfectly close to 100% geometric packing efficiency. They stack neatly like books in a library.
Whereas cylinders always leave gaps.
Cylindrical cells, no matter how tightly you cluster them, inherently leave about 9.3% of the available volume as just void space. It's unusable mass and volume that contributes nothing to the energy density of the system. In a highly space-constrained FSE chassis, that 9.3% advantage is enormous.
The SOR doesn't just mandate the type of cell. It provides supplier intelligence, which is invaluable for a new team. Who are the proven players in this space?
This is where strategy meets procurement. Molasta is the preferred recommendation, specifically their SLPBA series. They're well-established in Formula Student, they offer high-capacity cells, and critically, they offer customization of the tab locations.
And why is that important?
It allows the team to optimize the bus bar paths for that complex 140-force configuration. You can reduce bus bar length, which reduces resistance and weight.
And if Molasta is unavailable, who's the high-performance alternative?
Enertech is a very serious contender. They're known for supplying some of the most successful European teams.
And their specialty is low internal resistance.
They're known for achieving an internal resistance below 1.5 millions. The analysis shows that this level of efficiency means the cell generates only about 15 watts of heat at a 100 amp discharge.
Which is fantastic.
It's fantastic. It massively minimizes the load on that 1.0 kilowatt cooling system target we'll talk about later. COCOM is mentioned, but really only as a technical benchmark. They're often ruled out by very high cost and a high minimum order quantity, or MOQ.
Let's address the elephant in the room, though.
Yeah.
Cycle life. If these cells are so high C rate, they must have a really short lifespan. How does the SOR manage that?
They absolutely do. LiPo cells that are operating continuously at 40 C rates, they fail quickly. They often achieve less than 300 cycles before significant capacity fade or dendrite growth starts to compromise performance. And you cannot ignore this.
So what's the strategy?
The strategic recommendation is not to rely on a single set of batteries. It's what we call the two-pack strategy.
Set A and set B.
Exactly. Set A is the testing pack. It's the workhorse. It absorbs all the dyno runs, all the tuning, all the practice laps. It's designed to be used hard and fail relatively quickly.
And set B.
Set B, the race pack, is kept pristine. It's only brought out, charged, and installed during the competition week. The entire purpose of Set B is to ensure you have the absolute minimum internal resistance available when it matters most.
Maximizing power and minimizing heat during the final events.
That's the whole game.
And for fire safety, what are the mandatory requirements?
2 critical factors. First, all internal structural and insulation components must meet the UL94V0 flammability standard. That means they self-extinguish very quickly if they catch fire.
Okay.
But given the extreme thermal runaway risk with LiPo cells, the SRR suggests integrating thin mica sheets between each cell.
Mica.
Mica is an excellent thermal and electrical insulator. It's essential for suppressing a thermal runaway chain reaction. It prevents that fire from propagating from one cell to the next. It's a cheap, highly effective fire break.
Okay, we've settled on the cells and the segment constraints. Now, in the spirit of MECE, we need to finalize the overarching electrical topology subsystem 7.3 that governs everything. The requirement is 6.8 to 7.2 kilowatt hours of total capacity using a 144's 144 series configuration.
This defines our high-voltage architecture. With a nominal cell voltage of 3.7 volts, 144s gives us a nominal system voltage of 532.8 volts.
And we're circling back to hypothesis A here.
Exactly. The reduction in current this architecture provides is foundational to the entire lightweighting strategy. Lower current means lower resistive losses IR, and that allows us to hit our mass target using those aluminum conductors.
Let's focus on the capacity sizing. Why is 7.0 kilowatt hours considered the golden zone? It feels like such a precise target.
It is, and it's the result of detailed, experience-driven endurance calculation. An excellent FSE car consumes energy at a rate of about 0.28 to 0.32 kilowatt hours per kilometer.
Okay.
For the standard 22-kilometer endurance race, the theoretical consumption lands at around 6.6 kilowatt hours. You have to start there.
So the 7.0 kilowatt target provides a 0.4 kilowatt hour buffer, a 6% buffer. Is that enough?
That 6% buffer is mandatory insurance. You must account for 4 non-ideal real-world factors that can prematurely end an endurance run.
What are they?
First, capacity fade. The cells will degrade over the season. Second, cell imbalance. If one cell drops below the minimum cutoff voltage before the others, the entire pack shuts down.
Right.
Third, high temperature delay rating. Cells temporarily lose capacity if they run too hot. And fourth, the initial consumption of the formation lap, which is usually fast and very power hungry.
So the conclusion is,
Below 6.8 kilowatt is just too risky to guarantee a finish. Above 7.2 kilowatt is wasted mass that only slows the car down during the acceleration and skid pad events.
okay, here is where the high-stakes drama begins, the 600V compliance conflict. This tiny rule trips up entire teams, costing them a year of work. What is the danger here?
The FSG rules are absolute. The maximum tractive system voltage is 600 volts DC, period.
And our chosen 144's configuration when fully charged.
When fully charged to the cell's maximum open circuit voltage, or OCV, of 4.20 volts, calculates out to 604.8 volts.
That's a 4.8 volt overshoot.
It's a 4-volt failure point. It means immediate disqualification DQ during technical inspection. It's catastrophic.
So you have two options to manage this critical risk. The first is the software limitation strategy, or voltage capping.
This is the quickest fix. We just hard code the BMS firmware to limit the individual cell charge voltage. We must cap it at 4.16 volts.
And the math on that.
144 cells times 4.16 volts gives you a maximum pack voltage of 599.04 volts, safely under the 600-volt hard limit.
And the trade-off is you're sacrificing capacity by not charging all the way to 4.2 volts.
You are. You sacrifice maybe 3 to 5% of the total available capacity. However, since the capacity gain between 4.15 and 4.2 volts in a high C-rate LiPo is already minimal, this is a very acceptable low-cost compliance fix.
What about the second, more robust strategy, the hardware adjustment?
This involves permanently dropping 2 series cells, moving to a 142's configuration. At 142's, the absolute maximum voltage is 596.4 volts.
Which provides a 3.6 volt margin. Why is that margin so valuable?
It provides crucial safety space to absorb a transient voltage spike, which can happen during aggressive regenerative braking. If that spike pushes the voltage over 600 volts for even a millisecond, the pack can fault. 142's offers a critical buffer against those real-world electrical transients. The document strongly suggests this as the safest long-term path.
Beyond the cell count, the remaining high-voltage component requirements are equally stringent. Let's look at the accumulator isolation relays, or ARRs.
The ARRs are non-negotiable safety devices. They are the big electrical disconnect switches that isolate the high voltage from the rest of the car, and they must be rated for at least 600 volts and 300 amps to handle potential loads and faults.
And closely related is the pre-charge circuit.
Right. This circuit must complete its function, which is charging the massive motor controller capacitors in less than 500 milliseconds. If it's too slow, the main ARRs, when they close, face a massive damaging inrush of current.
And finally, the maintenance plug. This is a safety gate for the mechanics.
Mandatory for rules compliance. It must be toolless, finger-proof, and critically, it must be designed to segment the high voltage into safety blocks of less than 120 volts when it's removed. This ensures that maintenance staff can safely access the accumulator for inspection without needing specialized high-voltage insulated tools. It's all about personnel protection.
Now we move to subsystem 7.4, the structural side. This is where the battery box stops being just a container and truly becomes a safe deposit box, capable of surviving a massive high-speed impact.
The requirements are extreme, and they have to be the governing factor for the entire enclosure design. The box must withstand longitudinal and lateral 40G loads and 20-gram vertical loads.
Let's quantify that force. What does 40 GAM actually feel like for this box?
Assuming the highest end of our total accumulator mass, 75 kilograms, a 40-gram impact generates nearly 30,000 newtons of force.
That's over 3 tons.
Yeah.
Pressing against the box, trying to rip it from the chassis.
Exactly. And the ultimate goal of maintaining structural integrity under that load. It isn't just to keep the cells from flying out.
What is it then?
The ultimate goal is to prevent deformation. If the box deforms too much, the internal insulation distances, what we call creepage, along a surface and clearance through the air will fail. That leads to an immediate catastrophic internal short circuit. The structure must be rigid enough to maintain those microscopic safety margins under 3 tons of stress.
This level of performance requires specialized materials. The SOR mandates what it calls CFRP supremacy over standard aluminum. Why the shift to carbon fiber reinforced polymer sandwich structures?
Standard aluminum, while it's robust, is just too heavy for the required specific strength.
Specific strength being strength per unit of weight.
Correct. CFRP is about 40% lighter than common aluminum alloys for equivalent performance, and its specific strength can be 3 times greater. For a 6 kilogram segment and a low mass total enclosure, this advantage is just non-negotiable.
What are the other structural benefits of composites, beyond the weight saving?
You gain tailorability and insulation. CFRP offers superior electrical insulation, which reduces the need for additional heavy insulation layers inside. And crucially, the layup allows for anisotropic design.
Meaning you can orient the fibers.
It means the engineering team can directionally orient the carbon fibers to specifically reinforce the structure against the highest stress directions, the 40G longitudinal and lateral directions. You can literally steer the strength exactly where you need it most.
If the team does use CFRP, there's a specific safety requirement involving an internal aluminum layer. Why is that necessary?
That's a great question. Carbon fiber composite itself is generally insulating because the fibers are suspended in an epoxy matrix. However, if the box suffers damage or if the composite delaminates, if the layers separate, there's a slight risk of conductivity.
Okay.
To mitigate that risk and also to act as a shield against electromagnetic interference or EMI that could affect the BMS, the structure requires a mandatory 0.5 millimeters solid aluminum layer incorporated internally and grounded to the chassis. It acts as a permanent grounded safety shield.
Let's get into the specifics of the composite layout.
Yeah.
How do you construct a wall that resists such extreme forces yet remains incredibly lightweight?
The key is the sandwich structure. You use 2 thin, high-strength face sheets. T700 SC unidirectional fiber is specified, and you separate them with a thick, lightweight core.
And what's that core made of?
Typically Nomex honeycomb or high-density PMI foam ranging from 10 to 15 millimeter spec.
And why the thickness? Why that's so important?
Stiffness. The bending stiffness of a beam or a panel increases cubically with its thickness. So by having a thick, lightweight core separating 2 strong face sheets, you gain an exponential increase in your resistance to bending and buckling without adding significant mass. It's fundamental structural engineering applied to its highest degree.
Then you move to the hardpoint strategy, where the box actually bolts to the chassis. This is where the force is concentrated and where failure often starts.
It is. If you just drill a hole in that sandwich structure and bolt it down, you will crush the lightweight core and the structure fails.
So what's the solution?
The SRR mandates 2 solutions. Potting, which is filling the core space with a dense, high-strength mixture of epoxy and chopped fiber, or embedding solid metallic inserts, usually aluminum or titanium. These dense hardpoints ensure that when the mounting bolts are tightened or subjected to the extreme forces of a 40-gram impact, the panel doesn't crush or fail at its weakest point.
Finally, the verification plan. You can't just say the box is strong. You have to prove it for scrutineering.
This is the race before the race. The team has to start physical testing immediately on coupon samples that are identical to the final layup. They must conduct 3-point bending and perimeter shear tests to generate real, verifiable material parameters for the crucial structural equivalency spreadsheet submission.
And if you don't have that real test data,
Your SES will be immediately rejected, no question.
and the required simulation standard, the finite element analysis, or FEA, uses some highly specialized composite failure criteria, SAIWU or Hashin. What do these criteria predict that a standard analysis doesn't?
That's excellent context. When metal fails, we typically use the von Mises criteria to predict yielding. But composites, they don't yield in the same way. They fail by matrix cracking, fiber breakage, or most critically, delamination, the layers peeling apart. SAIWU and Hashin are specifically designed to model these failure mechanisms in layered materials. They are the gold standard for predicting exactly when the laminated structure will separate and cease to hold the 40G load. This allows the engineering team to design with a safety factor of at least 1.5 against catastrophic failure.
We transition now to Subsystem 7.5, zero-leak thermal and fluid engineering. The thermal requirements are strict, keep the cells between 25 and 40 degrees Celsius. This small window is vital, as any excursion above 60 degrees leads to rapid, irreversible degradation.
Managing heat is absolutely mandatory for endurance, but the first major mechanical challenge here is acknowledging that pouch cell breathing again. These soft pack cells, they expand when hot, contract when cold, and they experience permanent swelling over time. If we don't account for that movement, we compromise cell health and structural integrity.
So what's the engineering solution to manage this constant dynamic movement?
You have to introduce what's called a compliant layer. Typically, it's a special foam, like Roger Porin foam, and you place it between the cell and the cold plate.
And what does that foam do?
It serves a critical trio of functions. One, it absorbs that expansion tolerance, which maintains a constant stack pressure. That prevents internal cell delamination, which is a common failure mode. Two, it ensures excellent thermal contact despite minor dimensional changes. And three, it acts as an insulating barrier against thermal runaway propagation, adding a final layer of defense between neighboring cells.
And the cold plate itself must not be rigidly attached to the enclosure.
No, it can't be. The cold plate should be floating. If it's rigidly bolted down, the thermal expansion and contraction will stress the entire assembly. Allowing for minor controlled displacement accommodates the overall module expansion and prevents unnecessary stress on the cells, which could lead to physical damage or an increase in internal resistance.
Let's move to the non-negotiable requirement, the zero-leak strategy, which the doc describes as aeronautical-grade safety. You said coolant leakage is the single most common cause of high-voltage isolation faults.
And immediate DQ. The coolant is typically water and glycol, which is highly conductive. A single leak inside the high-voltage box means an immediate high-voltage isolation fault, or ISO fault. That mandates a shutdown. It's a terminal event for your race.
So the rule is absolute.
The mandatory requirement is that the in-box fluid path must have either no joints or it must use a double sealing design. There's absolutely no compromise here.
Explain solution A, the highly recommended path using continuous tubing.
This is the highest reliability path, but it's also the most difficult manufacturing challenge. It involves using a single, continuous piece of aluminum or copper tubing that is routed precisely through all the cold plates via controlled bending.
So you physically eliminate all the connection points inside the box.
You eliminate all cut ends, all standard pipe connectors, all potential leak points inside the high voltage enclosure. It's expensive and it demands perfect manufacturing quality, but the resulting system integrity is absolute.
But if the team prioritizes modularity, the ability to quick swap segments, which links back to that 6-kilogram operational advantage, they have to adopt solution B, the double sealing connectors.
This is the necessary compromise. It requires industrial-grade, dual seal connectors, like the ones made by specialized companies like Stavely.
And the mechanism is designed to plan for failure, right?
It's genius because it does. It uses a primary O-ring seal to contain the fluid, and then a secondary O-ring seal outside of that.
So if the primary seal fails, how does this prevent the catastrophic ISO fault?
That's the critical design element. Leak detection via a controlled leakage path, or what's called a weep hole. A small channel is engineered between the primary and secondary seals. If that primary seal fails, the coolant is routed through this weep hole outside the box.
So you can see the leak before it becomes a problem.
The leakage can be externally detected, either visually or by a simple humidity sensor, before the conductive fluid ever compromises the high-voltage components inside the enclosure. You detect the leak externally, and you can address it before the safety system trips.
Finally, the thermal sizing. Given the high C-rate cells, what's the heat load we must dissipate?
Based on the estimated 60 amp average current we expect during the endurance event, the baseline heat generation, that's IOU ISO-R again, is estimated at 777 watts.
But you have to factor in other losses.
You do. Factoring in losses from bus bars, contact resistance, thermal inefficiencies, the system must be capable of a sustained 1.0 kilowatt heat dissipation capacity.
And to handle that 1.0 kilowatt efficiently, the flow design is critical.
Absolutely. We have to minimize flow resistance. Parallel channels are strongly preferred over a serpentine flow because they minimize the pressure drop. The target pressure drop is less than or equal to 0.5 bar at a flow rate of 5 liters per minute.
And why is that so important?
Parallel flow ensures the fluid flows evenly across all the cooling plates. That guarantees a uniform temperature distribution across all 144 cells in the module, which is essential for maintaining cell health and consistency over the entire course of the race.
We finish with Subsystem 7, moving from this brilliant design to operational reality. The goal is achieving that quick 30-minute pit lane maintenance target through mistake-proof poka-yoke assembly.
Poka-yoke is all about designing the assembly process to prevent human error. If a technician is under stress in the pit lane, they should not be able to connect the module incorrectly.
And that begins with the 144's connections.
It does. Laser welding is mandated because compared to bolted connections, it is lighter, it provides superior electrical continuity, and most importantly, it creates a permanent joint that cannot loosen under race vibration. Bolted connections loosen. Welded connections do not.
The single most fragile element of the system seems to be the BMS wiring harness for the voltage and temperature acquisition. How do you protect that?
These harnesses are highly vulnerable to abrasion, damage, and electromagnetic interference. The solution is to use flexible printed circuit, or FPC, boards, or customized shielded wiring harnesses. And critically, these harnesses must terminate in positive locking connectors, like a Molex DuraClick.
And what do those do?
They clip in securely, and they provide tactile and auditory confirmation that the connection is made and, crucially, will not detach due to vibration or minor handling errors.
On the maintenance side, I love the concept of the inspection window for diagnostics.
It speaks directly to efficiency and safety. The high voltage box should never be opened unnecessarily. The inspection window, made of transparent polycarbonate, lets engineers visually check two critical internal parameters without breaking the safety seal.
What are they checking?
First, the humidity indicator cards, a simple visual check on the box's sealing integrity. And second, the general status of mechanical connections and internal components. It just speeds up technical inspection and preserves the integrity of the enclosure.
Let's address the bureaucratic phase. Regulatory compliance, or the race before the race. This involves the structural equivalency spreadsheet, the SES, and the electrical system form, the ESF.
Scrutineering starts months before the competition. For the SES, that physical test data for the CFRP panels must be generated and submitted early. If you submit a design that relies on theoretical numbers, it will be rejected. You might provide real material parameters.
And for the ESF?
The detail required is extreme. You have to provide clear professional schematics detailing the exact location, model, and most importantly, the braking capacity of every single fuse and every accumulator isolation relay. Incomplete or vague documentation dramatically increases inspection friction on-site.
And the final hurdle, notorious for disqualifying new teams, is the rain test strategy.
The design target is an IP67 rating that's dust-tight and resistant to water immersion. The sealing solution must be continuous EPDM foam seals, not liquid silicone.
Why not liquid silicone?
It's messy, it's hard to remove for maintenance, and it's prone to uneven application, which creates high-risk leak paths. EPDM foam, when it's properly compressed, is reliable and repeatable.
And how do we prevent the box from creating negative pressure as it cools, which could suck water past even the best seals?
That is the function of the Gore-Tex waterproof breathable valve, or breather.
A breather valve?
Yes. When the battery heats up, internal air pressure increases. When the car stops and the battery cools down, the air contracts, creating negative pressure inside that sealed box. This negative pressure can actively draw water past the seals, leading to failure. The Gore-Tex membrane balances the internal and external air pressure while physically repelling liquid water. It eliminates a major hidden failure point in competition.
We've taken a really deep dive into the HVA 7.0 requirements, viewing the entire project through the lens of a world-class strategic consultant. Let's summarize the core strategic pillars we've explored.
The entire HVA 7.0 system is, at its heart, an exercise in extreme, calculated trade-offs. It's built on a foundation of extreme lightweighting, that aggressive 6-kilogram segment target that buys you dynamic and operational advantage.
Right.
This is coupled with aeronautical-grade safety, which is proven by that 40G structural requirement and the non-negotiable zero-leak thermal strategy using double sealing.
And finally, high efficiency.
Yes. Driven by the 144's high-voltage architecture and the selection of those power-dense soft-pack cells.
So what's the ultimate trade-off that should stick with you, the listener?
I think it's that success in FSE is not about accumulating expensive parts. It's about expertly balancing energy, mass, and safety. This team, this plan, intentionally chose the most difficult structural path, that 6-kilogram limit, to gain the maximum dynamic advantage.
Accepting the complexity as the cost.
Accepting the complexity of a high-voltage BMS and advanced composites as the cost of competitive superiority. The design reflects an uncompromising vision where engineering difficulty is just. It's viewed as the price you pay for a world-class lap time.
The strategic vision laid out in the document is very clear. For commercial EV, the mission might be win on Sunday, sell on Monday. But for this team, the mission is different. Win in design, finish in endurance.
And this raises our final provocative thought. The entire strategy is predicated on surviving that 22-kilometer endurance event. That's the final test of reliability. So what specific engineering decisions, some seemingly small, made way back in the design phase, ultimately determine whether this world-class electric powertrain can survive that grueling final event. Consider specifically how that generous 6% energy buffer, which might have seemed like overkill, and that mandatory 4.16-volt voltage cap, which sacrificed immediate capacity for compliance. How do those two things directly impact the car's ability to cross that final finish line without a terminal voltage sag or a thermal shutdown?
So those early quiet trade-offs are the real determinants.
They are the true determinants of the final outcome.
A compelling point. Every gram and every volt matters. We'll leave you to mull over those critical design choices. That's it for this deep dive. We hope you feel significantly more well-informed.
Until next time.